Hello everybody. The topic which I am going to explain you in this video is about the scalar product and Hermitian conjugate in quantum mechanics. So we know that every quantum mechanical system will have something called state. It could be a function or it could be also a vector. So sometimes we call it as state function and sometimes we call it as state vector. So if we take two state functions of a quantum mechanical system as let us say psi and phi, then of course these will be functions of coordinates like x, y, z, and the scalar product of these two state functions, which we actually denote by putting them in a open bracket like this and separating them with a comma. This is actually how we denote scalar product of state functions psi and phi, and it is defined through a volume integral. It will be actually kind of a triple integral involving integral for x, integral for y, and integral for z, with the limits from minus infinity to plus infinity. So let me write that in mathematical notation. So it is actually a volume integral. For x it is actually from minus infinity to plus infinity, and for y also it is from same limit to same limit, and for z is also the same. And in the integrand what we will have is we have this psi star and then phi here, and then it will be dx, dy, and dz. This is the definition of scalar product of two state functions. And in case if we have the states represented as vectors, so let me actually say that psi could be something like a1, a2, a3, and if phi was something involving b's like b1, b2, and b3, then the scalar product of psi and phi, if we actually write again with the same notation, then it will be actually, first we write this one, but it will be actually like a row vector and also involving the complex conjugates a1 star, a2 star, and a3 star, and after that we'll be writing phi as it is involving b's, b1, b2, and b3. So this is a definition of scalar product if we actually designating the states as vectors, and this is a definition if we are designating the states as functions. So this is actually the definition of scalar product of state functions and state vectors. And let me actually quickly go into defining Hermitian conjugate. That means let us say that we have got let us say that we have got some operator A, and if operator A, for that operator A, its Hermitian conjugate is actually defined using the rule for scalar product. So let me say that if we have something like psi and some operator A and its Hermitian conjugate, we actually say A dagger. So if we have an operator A, its Hermitian conjugate is called A dagger, and the way we designate, we denote that is by writing A and on top of that this symbol dagger, just like the knife with the handle kind of thing, small knife, it's called dagger. And A dagger phi, it is defined like this, so it will be A psi with phi. This is the definition of Hermitian conjugate for some operator A. So A dagger is defined through the definition of scalar product of two state functions. So let me actually put subheadings here. All we were discussing here was actually scalar product of 5, and here it is actually this Hermitian conjugate defining using the definition of scalar products. So this is the definition of it, and in case if you have the states as vectors and then the operators as again matrices, square matrices, then we should be actually knowing that a dagger is actually kind of a dagger is actually complex conjugate of A, and on top of that transposing of that. So a dagger is simply a complex conjugate and transpose of the resultant matrix. So let me actually define A in terms of something like A1, A2, A3, B1, B2, B3, C1, C2, C3. Then if you have it like this, then a dagger will be, first we have to do the complex conjugate of all these things. That means we'll get A star, A1 star, A2 star, A3 star, B1 star, B2 star, B3 star, C1 star, C2 star, C3 star, and after that we should transpose it. So that means we'll get A1 rows will be actually columns now. So we'll get A1 star here, A2 star here, then A3 star here as the first column, then we'll get B1 star, B2 star, and B3 star as the second column, and then finally the last column will be C1 star, C2 star, C3 star. So this is actually how we actually finding Hermitian conjugate of some operator when it is in matrix form. And if it is actually kind of in a functional form, like if the operator was actually like some kind of differentiation operator or something, then we should be using the definition of scalar products to actually define a dagger for it. And after defining Hermitian conjugate, I will tell you some important kind of operators which are called Hermitian operators. So they are called Hermitian, 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 Hermitian operators, operators. They are actually the ones for which if you find the a dagger, then the result will be the same as initial A. So a dagger if you find and if you get the same thing as A, then of course they are operators, so we should be using kind of hat on top of them just to actually say that they're operators. And same definition we may use over here also. A dagger, I mean a hat dagger is a hat. This is the definition of it. Hat for operators. Okay, so in this video what we have done is we have defined scalar product of two state functions or maybe two state vectors. Then we defined Hermitian conjugate, and using that we defined Hermitian operators. And the reason why we worry much about Hermitian operators is that in quantum mechanics all the physical observables will be actually our Hermitian operators, including position, maybe momentum, force, energy, all those things will be actually our Hermitian operators in quantum mechanics. So anyways, we'll know more about Hermitian operators in some other next video. And in this video I just wanted to talk about these facts, and I hope I made some convincing comments here, and I'll meet you next time with some other video. Thanks for watching. Bye bye.